let's talk about cross-validation. So what's the big idea? So we've determined that it's sensible to use a test set to calculate metrics like prediction error. And why is that true? How have we done this so far? Well, it's true because basically using the test set is going to allow us to get to sort of find that sweet spot between bias and variance, or to ensure that we're not overfitting our models. And so far, we've talked about doing this by basically finding some outside data, some new data to be able to test our model on that we fit with some training data. But what happens if we don't have a separate data set to test our model on? And this is very frequently the case. It's not so often that you have kind of two totally separate data sets that you can train your data on one and test on another. And so we can use something called resampling to estimate this test set prediction error instead of basically using a brand new test data set. We can use this method to be able to estimate that same prediction error and still be able to sort of strike that balance between bias and variance in a good way. Okay, so training error versus testing error. What is the difference? Which is typically larger? Well, training error is calculated by using the same observations to fit the statistical learning model. And so this is basically sort of double dipping. You're fitting your model on a set of observations, and then you're testing how well your model did on that same set of observations. Test error, on the other hand, is calculated using a statistical learning method to predict the response of new observations. And so this is sort of the more proper way to be able to estimate error, because you're using a separate set of data than what you used to fit your original model. And so the training error rate typically underestimates the true prediction error rate. So the training error rate is typically smaller than the test error rate, and therefore it underestimates the true prediction error rate if we were to get some new data. And so this plot basically recreates some of the plots that we talked about 2 lectures ago, where on the x-axis here I have model complexity or model flexibility from low to high, and on the y-axis I have the prediction error. And so over here on this side of the plot we have high bias and low variance. On this side of the plot we have low bias and high variance, and basically we're trying to strike this balance between the two. And so you'll notice this orange line here, the training sample, it's always getting smaller. And so regardless of basically how complex our model is, this training, the error for the training data is always going to get smaller as we move across this axis. And that's because we're just getting more and more overfit. We're basically, as we get really far over here in the complex or flexibility, we're basically just playing connect the dots between the points in our training data. And so we'll end up with very low prediction error, but it's not really representative of what would happen if we saw a new data set. Meanwhile, in the test data, we expect this U-shape relationship where we have pretty low complexity, we would expect higher prediction error. When we have very high complexity or high flexibility, we also expect high prediction error. And we expect that there's some sweet spot in the middle that kind of balances this bias and variance appropriately to kind of find the right model complexity. So estimating prediction error. Best case scenario, we have a large data set to test our model on. But this is not always the case, and in fact, it's often not the case. So let's find a way to estimate the test error by holding out a subset of the training observations from the model fitting process. And then we can apply statistical learning methods to those held out observations and see how well our model does. And so there's a couple approaches here. The first approach that we're going to talk about is called a validation set. And so with the validation set approach, you randomly divide the available set of samples into 2 parts, a training set and a validation set. And then you fit the model on the training set, and then you calculate the prediction error on the validation set. And so basically what we've done is we've created a test data set from our initial data. So we started with just a single data set, But before we did any model fitting, we split it into a training data set and a validation data set. We fit the model only on the training set, and then we tested the model. We calculated that prediction error on the validation set. If we have a quantitative predictor, what metric do you think we use to calculate this test error? We often use mean squared error to do this. And if we have a qualitative predictor, so something like a classification, we use misclassification rate. So this is what that looks like. So here, my blue squares, let's pretend like I have this data sample. And in my sample, there are 20 observations. And so I get this sample, and I randomly decide that half of them are going to be used to fit my initial model, and half are going to be used to test my model. And so I've done this random sampling. The blue end up being the ones that I use to train my model. The orange end up being the ones I use to test my model. And so on those, if our outcome is continuous, then I use the mean squared error of my validation set, or of this test split. So just take the mean squared error from my orange squares here, or my orange samples. And so what that means is I'm averaging over my test data y minus my predicted value of y squared. If I'm doing a classification problem, then instead of calculating this mean squared error, I'm just going to calculate the misclassification rate. So I'm still going to average over those orange test samples, but now I'm just looking at the indicator that yi is not equal to the classification that I give it based on my model. So my models, this F hat and the C hat, those are calculated, those are trained using the blue data, but then my prediction error is calculated using just the orange data. So here's an example from some data in R. So I have 392 observations in this auto data set, and I'm trying to predict miles per gallon using a variable called horsepower. So I have a bunch of data from 392 different cars, and I want to know if all I know is the car's horsepower, can I predict its miles per gallon? And so I can split the data in half and use 196 of those observations to fit my model, and then I can use 196 of the observations, the remaining 196 that were not used to fit my model, to test my model. And so when I do that, I get this graph where here on the x-axis I have the polynomial degree, which this is a form of flexibility. So as we're moving across this axis, my model is getting more flexible. And on the y-axis, I have mean squared error because my predictor of interest, miles per gallon, is continuous. And so since I'm using this validation set, I do end up getting this little bit of a U shape where when I have a very inflexible model, I've got a higher mean squared error. And you'll notice over here where I'm getting super flexible, the mean squared error ends up going up a little bit. And so there's probably somewhere here in the middle that's kind of the sweet spot flexibility. So as opposed to doing just this one time where we just take this validation set approach and we pull out our blue samples to fit our training data, to fit our training model on, and our orange samples to test our mean squared error on, we could do this multiple times. And so we could run this random sample where we pull out a subset of the data each time, where we've got a validation set and a training set, and these would be different observations every time. So we could do this multiple times and see how that looks. And so coming back to my auto example, I have still 392 observations. I'm trying to predict miles per gallon from horsepower, but now I've split the data in half many times, and I end up with a slightly different graph each time. And there's actually, so the shape of these graphs looks pretty similar, but there's definitely some noticeable variability in this mean squared error here. And so maybe we can do a little bit better than just this first approach in this validation set. And what I mean by better is, it'd be nice if the value that we got was a little more consistent, or there was less spread between each of the different runs that we did. So the drawbacks of the validation set is that this validation estimate of the test error can be highly variable, as we saw in that last plot, depending on which observations are included in the training set and which are included in the validation set. In the validation approach, only a subset of the observations, those that are included in the training set rather than the validation set, are used to fit the model. And therefore, the validation set error may tend to overestimate the test error a little bit for the model fit to the entire data set. So let's try a slightly different approach. This is called k-fold cross-validation. So it's a similar approach, but with some slight improvements. And so instead of dividing my data in half, I'm going to randomly divide my data into k equal-sized parts. I'm going to leave out part k and fit the model to the other k-1 parts combined. So for example, I could divide my data into 5 equal-sized parts, and I might leave out part 1 and fit the models to parts 2 through 5. And then I can obtain predictions for the left out kth part. So I fit my model. My model was trained on parts 2 through 5, but then I calculate my prediction error using part 1, so that left out kth part. And I'm going to redo this for each part, k1 through k, and then I'm going to combine the result. So this is what that would look like. So for example, here I'm doing 4-fold cross-validation. So I have 20 data points, and 5 of them are in each of my k folds. And so my first split looks like this, where these 5 here are, these 5 were randomly selected to be in my test data, and these 15 are in my training data. And so I fit my model to these 15 samples, and then I calculate my mean squared error on using just these 5. And then I do it again. And so the second time, I fit my model to these 15. So now I fit it to the 5 that I had previously used as my test data, and then these 10 at the beginning. And now I've left out this middle chunk here, these 5, the orange 5. And now I fit this second model, so I'm fitting it on these blue points, and I'm testing it, or I'm calculating my mean squared error using just these 5 left out points. And then I do the same thing again. Only this time, I fit my model to this training data, these blue points, the 10 over here and the 5 over here, and I calculate my mean squared error using just these 5 left out pieces. And then finally, I use my kth set here. I fit it to these 15 blue points, and I test my model using these 5 here. So I've got these 4 estimates of the mean squared error taken over each of my k folds. And now I'm going to take the average, or the mean, of these together. So I'm going to just take the average across all 4 of these to get my overall test error. And so written a little bit more mathematically, we basically split the data into k parts, where C1, C2, Ck indicate the indices of the observations in part k. And so my cross-validation error is just going to be the sum from k equals 1 to k of nk over n times the mean squared error of k. And so basically this is just the same as taking the average across each of those k mean squared errors. And the mean square error of k is going to be that same, this is that same estimate that we had given before for basically y, our observed outcome, minus y hat, our estimated outcome squared. And nk is going to be the number of observations in group k, and then of course y hat I is the fit for observation I obtained from the data with the part k removed. Now if we set k equal to n, we have n-fold cross-validation, which is actually a special case that we call leave one out cross-validation. And so using our same pictures, leave one out cross-validation looks like this. And so if we had 20 data points in our data set, leave one out cross-validation would fit the model to 19 of them, leaving one out, calculate the mean squared error using that 1, and then we do the same thing, leaving the next one out, and the next one, and the next one, all the way down until we'd done it with the entire data set. So we would do it n times, where we one at a time left a data point out and calculated the mean squared error for that data point, and then averaged across all of those. So picking k, K can vary from 2, which would be like that validation set that we talked about, splitting the data in half each time, to N, which would be leave one out cross-validation. And of course, this is going to be, this kind of is going to get at that bias variance trade-off that this whole class basically talks about a lot. But leave one out cross-validation is sometimes useful, but it usually the estimates from each fold are very correlated, which means that their average can have high variance. And so a better choice of K tends to be somewhere in the middle. I often pick something like 5 or 10 for my Ks. But again, this is going to get at that bias variance trade-off. So since each training set is only K minus 1 over K as big as the original training set, the estimates of prediction error will typically be biased a little bit upwards. This bias is minimized when K equals N, so leave one out cross-validation. But as I mentioned on the previous slide, because these are highly correlated, this has high variance. And so K equals 5 or K equals 10 basically provides a nice compromise for this bias variance trade-off. And so coming back to this auto example, where we had 392 observations and we're trying to predict miles per gallon from horsepower. In this first example, we have a 50-50 validation set, which is basically equivalent to twofold cross-validation. And you'll notice here we have a lot of kind of variability between each of these estimates, which is not ideal. As opposed to over here, where we have tenfold cross-validation, we see much more consistency between the estimates. And so we can feel more confident in any one of these that it's basically going to be similar to any other one. So we wouldn't need to basically redo this process multiple times. So estimating prediction error for qualitative outcomes, the premise is the same as cross-validation for quantitative outcomes, except now instead of calculating the mean squared error when you split your data into K parts, you're just going to calculate the misclassification rate. And so again, this NK is going to be the number of observations in group K, and Y hat I is going to be the fit for the observations. So there you have it. That's cross-validation. This is going to be really useful. All of the models that we fit, we're going to use cross-validation to basically help us decide the flexibility that we need, especially if we don't have a test data set, which often we don't.